Hi, everybody, and welcome back for Lesson 11 from Unit 6, which is all about accumulation functions. So, in our last lesson, we were introduced to the idea of an accumulation function, which is any function that is defined as the integral of a different function. Today, we're going to be looking at three different learning targets related to this specific type of function. The first learning target is I can apply the fundamental theorem of calculus to find the derivative of a function that is defined as an integral, or in other words, as an accumulation function. Now, this is actually a review learning target. We practiced it yesterday, where we were taking the derivative of accumulation functions by recognizing that the final answer was going to have the same function as the original with just the bounds plugged in times the chain rule. The second learning target for today is I can perform operations on accumulation functions. So this is going to be things like finding values for specific values for accumulation functions. And the last learning target for today is I can interpret the behavior of accumulation functions. So interpret the behavior of accumulation functions given graphical, numerical, analytical, and verbal representations. So this is going to be an example where we're going to be looking at features of functions, which we've talked about before, increasing, decreasing, critical points, concave up, concave down, etc. And we're going to be looking at those features of accumulation functions. So let's start with just redefining what an accumulation function is, just so we're all on the same page. An accumulation function is a function f where the function itself is defined and can be calculated by finding the area between the curve of g of x and the x-axis between a and x. So this is f of x is an accumulation function here. And the reason that f of x is an accumulation function is because to find values to calculate f of x, you need to integrate or find the accumulated area of a different function, g of x. So the first thing we're going to do is look at it's actually operations on accumulation functions. It's the second learning target where we are going to start with that because I want to make sure that we know how to work with and evaluate these functions. So let's let g be the function given by g of x is equal to the integral from 2 to x of f of t. And we've got the graph of f. So you'll notice f is inside of the integral. We have the graph of f, and we're going to use that to help us find values of g. Evaluate each of the following. For part A, it says find g of 0. Now, the first step here is to remember that anytime I say find g of 0, that just means plug in 0 into the equation. And so in this case, finding g of 0 means finding the integral from 2 to 0 of f of t dt. Now, in order to find an integral, we need to remember that that means find the area between 2 and 0. Now, between 2 and 0 would be this area on the graph. But the other thing we need to remember is that the bounds here are in the wrong order. You'll notice that in this problem, the lower number is on the top and the higher number is on the bottom, which means we're going to the left. We're going from 2 to 0 instead of from 0 to 2. What that means is that even though this area is above the x-axis, because we're moving in the left direction, we need to count this as a negative area. So to find this area, I would use my area formula for a triangle. So it would be negative 1/2 times the base, which is 2, times the height, which is 4. And that means my final answer would be negative 4. Again, the reason that this ends up being a negative area is because of the direction where the lower numbers on the top and the higher numbers on the bottom are going to the left. All right, that's the first example of finding a value using an accumulation function. Problem B here says find g of 2. Now, g of 2 means find the integral from 2 to 2. You'll notice I'm replacing the x with a 2 of f of t dt. Now, what you should notice here is that once you plug in the number 2, the bounds are the same on the top and the bottom. So we're not, like when we are integrating, we're not accumulating any area here because you're starting at 2 and you're stopping at 2. That means that the answer is 0, and that is one of our properties of integrals where the lower bound and the upper bound are the same number. The area accumulated is 0. For problem C, it says find g of 1. Now, g of 1 means find the integral from 2 to 1 of f of t dt. Now, similar to letter A here, going from 2 to 1, where 2 is the lower bound and 1 is the upper bound, those bounds are in the wrong order. The lower number is on the top, even though it should be on the bottom. So that means we're going to the left. That means that even though this area is above the x-axis, it's going to count as a negative area because of the direction. So that shape is a trapezoid. I'm going to find the area by doing negative 1/2 times the height, which is 1. It's the distance between these parallel sides. And then base 1, which is 2, and base 2, which is 4. Now, when I actually do that computation, I end up getting negative 3 because 2 plus 4 is 6, and half of that would be 3. Last but not least, let's find g of 6. So g of 6 means find the integral from 2 to 6 of f of t dt. Now, integrating from 2 to 6, this time we are actually moving to the right, which is the correct direction. So this is going to be a just kind of traditional area problem. Since this area over here is above the x-axis, that part of the area is going to count as a positive. So 1/2 times base times height minus this area is below, so that area is going to count as negative 1/2 times 2 times 1. That means I'm going to get 4 minus 1, which is 3 as my final answer. So that is kind of some operations finding values using accumulation functions. The next thing that we're going to be looking at are some features of accumulation functions. So I want to start by just reviewing some vocabulary that we have that we use to describe graphs. We talk about critical points, increasing and decreasing, points of inflection, concave up, concave down, relative maximums, relative minimums, and then absolute extrema. This is a brief review of all of that vocabulary and the definitions. I'm not going to go through that right now because it is something that we've learned before, but I did want to put this back in your notes in case you want to go and review it on your own, since you will need to understand these words, the vocabulary words, as well as the definitions in order to do the next few problems. So before we jump in, one thing that's really important is to realize that in order to find any of this information, you have to be able to find the derivative. Whether it's the first derivative or the second derivative, you have to be able to find the derivative. So what we're going to do in these problems is we're going to practice finding both the first and the second derivative of these functions, because ultimately we're going to need to know how to do that in order to answer questions about where these functions are increasing, decreasing, concave up, concave down, critical points, points of inflection, and extrema. So for this first problem, we are going to take the derivative using the fundamental theorem of calculus, and we are going to find both the first and the second derivative. So to find the first derivative, f prime of x is equal to, what the fundamental theorem of calculus says is that since we're taking the derivative of an integral, and derivatives and integrals are in a lot of ways inverse operations, we're going to end up still having g of something, but the only change is going to be we're going to plug in the x. So it's going to be g of x instead of g of t. Now, we're not going to worry about the 2 because the derivative of a 2 is 0, and so that's not going to affect our answer. And normally we would incorporate the chain rule, but the derivative of x is just 1. So since the chain here is just 1, you don't really need to write it. You could if you wanted to, but it's unnecessary. Then we are also going to find the second derivative. So the second derivative here means starting from what we just got, take the derivative again. So the second derivative would be, the second derivative of f means I have to take the derivative of g of x, and the derivative of g of x would just be g prime of x, and that's my answer. So now I know that the first derivative of f is just g, and the second derivative of f is g prime. For the second question here, we're going to take the first two derivatives. So the first derivative, I'm going to find f prime of x. Like I said before, the fundamental theorem says that when you take the derivative, the g function just stays the same, and you end up plugging in your bound, which is 4x. And then we need to do the chain rule. Now this time, since the chain is not 1, it's 4, we need to actually write it down, which means my simplified derivative function would be 4g of 4x. Now to find my second derivative here, so the second derivative of f, I need to find the derivative again. Now in this case, I'm going to need the chain rule again because 4x is inside of that parentheses. So I'm going to start with the outside, g prime, leave the inside alone, 4x times 4. And then I can simplify. So 4 times 4 is 16. And then times g prime of 4x. So I've got my first two derivatives here. For my next problem, I'm going to go ahead and take, again, the first two derivatives. So the first derivative is going to be the derivative of 6x, which is just 6, plus the derivative of the integral. The integral and the derivative are inverse operations, so I'm just going to have g of, and I'm going to throw in my bound, which is x. Again, the chain here would be 1, so we don't need to write it. We can just go ahead and leave it off because it's unnecessary. You can write times 1 if you want to, if that makes you happy, but you don't have to. Now my second derivative here, f double prime of x would be equal to, the derivative of 6 is 0, and the derivative of g would just be g prime, so it would just be g prime of x. Okay, that pretty much finishes up the operations that we need to know how to do with accumulation functions. We know how to find values, and we know how to find the first and the second derivative. Now we're going to use those operations and what we know about functions, and we're going to analyze accumulation functions. So accumulation functions and graphs. Let f be a function defined on the closed interval from 0 to 7. The graph of f consisting of 4 line segments is shown. Let g be the function given by g of x is equal to the integral from 2 to x of f of t dt. Now, this is a very typical AP FRQ. So this is really important. As soon as I see this, as soon as I see that I have an accumulation function, my advice to you would be before you do anything else, immediately take the derivative and take the second derivative to make sure that you have those written down because you are going to need them for sure throughout the entire problem. So before I even read the questions, as soon as you see an accumulation function, I would write down g prime of x, which in this case, using the fundamental theorem, the f would stay the same, and I would just plug in the x, and then g double prime of x. And again, that would just be f prime. These three functions, g prime, and g double prime, are really going to be necessary for this entire problem. So I like to start by just writing them all down right away. Now, problem A here says find g of 3. So to find g of 3, and how you show your work here is important because on the AP test, you need to show your thinking. All you're going to do is take the number 3 and plug it into the integral. So it's the integral from 2 to 3 of f of t dt. Now, the integral from 2 to 3, if I go to this graph, is going to be the area, because this is the f of x graph, is going to be the area between 2 and 3, because an integral means find the area. So in order to find that area, I'm going to find the area of the trapezoid. I'm going to have 1/2 times the height, which in this case is the distance between the two parallel lines, so 1, and then base 1, which is 4, and base 2, which is 2, which is going to give you 3. Okay, next it says find g prime of 3. Now remember how we went and we wrote down our functions here? This is where that's going to be really helpful. So g prime of 3 means take the number 3 and plug it in. So I'm just going to be finding f of 3. Now f of 3 just means find the output value of f. when x is equal to 3? F of 3 is literally just what's the output. So on this graph, when x is 3, the output is 2. So my answer would be 2. And last but not least, g double prime of 3. Again, remember we wrote down those functions. That's going to be very helpful here. So g double prime of 3 is equal to f prime of 3 because g double prime is f prime. F prime of 3 means the derivative of f. So it's the slope when x is equal to 3. Now on this graph, the number 3 is on this line segment that's part of the graph, and the slope of that line segment can be found by doing rise over run. In this case, it would be negative 2 over 1. So my answer would just be negative 2. Okay. Next, we're going to make things a little bit more complicated. So instead of just operations where we're finding values, we're using the relationship between g and f. We're going to need to identify where g is increasing and decreasing. So these are those features of functions. As soon as you see the words increasing and decreasing, you need to know that you're thinking about where g prime of x is greater than or equal to 0 and where g prime of x is less than or equal to 0. Now, in order to do this, in order to identify where a function is increasing and decreasing, we always start by taking our derivative and setting it equal to 0 to find the critical points. So I'm going to go back to the definition of my derivative, which, as you can see up here, g prime is f. So g prime of x is equal to f of x is equal to 0. Now, what you'll notice is that this is telling me that f is really g prime. So this is the same thing as looking at the graph of the derivative of g. You're looking at g prime, which we've done before. That means that we are going to be finding where this function is equal to 0. The critical points are going to be at 4 and at 6. That's where it switches. Now, the second thing we're going to do is make a table of values, which means this graph goes from 0 and then 4 and then 6 and then 7. From 0 to 4, the graph is above the x-axis, so the original function is increasing. From 4 to 6, the graph is below the x-axis, so the original function is decreasing. And from 6 to 7, it's back above. So we would say that our function is increasing on the intervals from 0 to 4 and also from 6 to 7 because, and here's where we need to pay attention. This is kind of the same thing we've done before. It's where is the graph above, right? Above is increasing. Now, how we say our answer here changes a little bit from what we did when we just had the graph of g prime. Because this is a relationship between g and f, like this is f and this is g prime, the way we say our answer here is because g prime of x, which is equal to f of x. So we're showing that relationship is greater than or equal to 0. Now we're also going to say decreasing on the interval from 4 to 6 because g prime of x, which is equal to f of x, is less than or equal to 0. Normally, we would just say g prime is greater than or equal to 0, but we need to kind of show that relationship between g and f, since that's what makes this problem a little bit different than if I just said this is the graph of g prime from the beginning. You're kind of using your knowledge about derivatives to build that relationship here. So that's the piece that is new, is that you have to say this piece right here, that g prime, which is equal to f of x. You want to show that relationship between g and f. Okay. Next, it says find the x-coordinates of the critical points, determine whether each of these points is a relative max, min, or neither. So for critical points, we are looking for where the derivative, which is equal to f of x, is equal to 0. So that would be at 0 and 4 and 6. So we would say at x equals 0, 4, and 6, because g prime of x, which is equal to f of x, is equal to 0. Next, we want to determine whether each of those is a relative max, min, or neither. So for the second part of this, we're going to go through these one at a time, and I should use purple. We're going to determine if it's a max, a min, or neither. So at x equals 0, we would say it is neither a max or a min, because the derivative, which is equal to f of x, does not change signs. At x equals 4, if we look at the graph, we're changing from above to below, which means we're changing from a positive to a negative slope. So that's going to be a max. There is a relative max because the derivative, which is equal to f of x, changes from positive to negative. And last but not least, at x equals 6, we would say that there is a relative min because the derivative, which is equal to f of x, changes from negative to positive. Okay. Now, more features of functions based on using this relationship. So I'm going to go ahead and write the g prime of x is equal to f of x again here. It's a continuation of the same problem, but since it's on a different page, it's going to be handy to have these things written down. Okay. Next it says, find the x coordinates of the points of inflection. Explain your answer. As a reminder, points of inflection are the places where the second derivative changes signs. Now in this problem, the second derivative is equal to f prime of x. So we're looking for where the slope of this graph changes signs, which if you think back to when we looked at the graph of the derivative, that's the same thing we looked for before. So our points of inflection would be at 2 and 5. So we would say x equals 2 and 5 because the second derivative, which is equal to f prime of x, changes signs. Next, it says determine where g of x is concave up and concave down. So concave up is going to be where the second derivative, which is equal to f prime, is greater than 0. And concave down is going to be where the second derivative, which is equal to f prime, is less than 0. So we're looking at the slope of this graph where it's a positive and a negative slope. So we're going to say concave up from 0 to 2, and we're going to use open brackets here, and also from 5 to 7, because g double prime of x, which is equal to f prime of x, is greater than 0. And we're going to say concave down from 2 to 4 to 5. So 2 to 5, because g double prime of x, which is equal to f prime of x, is less than 0. And last but not least, find the absolute maximum and absolute minimum. Now, anytime I ask you about the absolute maximum or the absolute minimum, you need to use the candidates test, which means that you are considering the critical points as well as the endpoints. Now, in our previous problem, we said that the critical points were the x-intercepts, and we're also going to include the endpoints here, so 0 and 7, because those are potential locations of maximums and minimums. So we're going to have x, and we're going to have to find values of g of x. in order to determine who's really the biggest and who's really the smallest. So my critical points / endpoints would be 0, 4, 6, and 7. To find values of g of x, we need to go back to the definition of g of x. So to find g of 0, we're going to do the integral from 2 to 0 of f of t dt. Now on this graph, the integral from 2 to 0, because you're going backwards, it's going to be the area of this first big triangle here, but it's going to be negative because you're going backwards. So it's going to be negative 1/2 times the base is 2 times the height is 4, which means you get negative 4. For the next part, we're going to be finding g of 4, which is going to be the integral from 2 to 4 of f of t dt. Now that's going to be a triangle that's the same size, but going the other direction. So it's just going to be positive 4. I can use my work from the first answer to get that one. G of 6 is going to be the integral from 2 to 6 of f of t dt, which is going to be the triangle I just found minus the triangle that's below from 4 to 6. So it's going to be 1/2 times the base times the height, which is going to be 3. And last but not least, the integral from 0 to 7, which is the integral from 2 to 7 of f of t dt, which is going to be the area I just found plus that little triangle that's above. So 1/2 times 1 times another 1, which is going to be 3.5. What that means is that the absolute smallest that this goes, the lowest number, is going to be at 0. And the highest that this goes is going to be at 4. So I'm going to say that there's an absolute min value of negative 4 at x equals 0, and there is an absolute maximum value of positive 4 at x equals 4. Okay, that is it for today. Thank you guys so much for watching, and I'll see you soon for some practice.